So we mentioned in the previous video that the axiom of completeness is a statement about sets being bounded and having lower bounds. Now we need to, or upper bounds, we need to actually define what these things are before we can make any sense of it. So this video is going to mostly be some definitions, and then we'll explore a couple of short theorems at the end to just explore how we work with them. So let's look at the definition of a set being bounded above. It's a fairly precise definition, and one of the things in this course that you need to become really comfortable with is knowing the details of these definitions, because we need to be careful when we apply them that we know all the details. So this definition tells us what it means for a set of real numbers to be bounded above. And essentially it says if you can find a number that is greater than or equal to all of the numbers in your set, then that number is called an upper bound for your set. So let's just draw a number line over here. Let's say my set of real numbers just looked something like this. Here they are. So here's my set A. Now there are lots of different upper bounds. This is an upper bound. Any of these numbers, so long as they're greater than or equal to every element in my set A, these are all upper bounds. And if one of these or more exist, then we say that the set is bounded above. And we can make a similar statement for a set being bounded below. If there exists a lower bound, then we say the set is bounded below. If we just say that the set is bounded, then that means it's bounded both above and below. And this leads us to our next definition, which is of these upper bounds, we call a number S the least upper bound if A, it is an upper bound for A, and B, if you choose any other upper bound, or any upper bound at all, then the number S is less than or equal to B. Okay, so least upper bound is a two-part definition. So to demonstrate that something is a least upper bound for a set, you need to verify that it satisfies both of those properties individually. Now this has a name that we usually call it, and we usually call it the supremum of the set. So this is usually called the supremum of A, and we write it using sup. Okay, so whenever we refer to sup A, which is just a shorthand for the least upper bound of your set A. Okay, and just like for upper bounds, we can define lower bounds as well, and the greatest lower bound is a similar thing. So the greatest lower bound which is called the infimum, is defined similarly. In fact, a useful exercise would be can you write down the precise definition of the infimum, and is denoted by inf. Okay, so there are our two things, sup A and inf A, least upper bound and greatest lower bound, respectively. Okay, so to make sense of these definitions, let's just have a quick look at a couple of sets and see what we can say about the supremums, or suprema and infima of these sets, and whether or not they exist. So I'm going to have a set S1 is the set of all values of x, such that -3 is less than or equal to x is less than or equal to 7. Okay, so just a couple of statements. If we want to list off some upper bounds, well, we have 10, 7, 8, 6, 6.1 are all upper bounds. No, not the 6s. 9, 9.1 are all upper bounds for S1. Okay, because every element of S1 is less than or equal to them. The supremum of S1, the least of these upper bounds, is 7. You can't have an upper bound that's lower than that. So S1 is bounded above and below, which means we can find an upper bound and a lower bound. And similarly, we can say that the infimum of S1 is -3. Okay, in this case, inf S1 and sup S1 are elements of S1 itself. But that's not necessarily the case if we consider S2 to be the set 3 plus 1 over n, where n is a natural number, okay, 1, 2, 3, 4, 5, etc., which equals 4, 3 1/2, 3 1/3, 3 1/4, etc. Then if we try and look at the supremum and infimum of this set, hopefully it's fairly easy to see that sup S2 equals 4, which is an element of S2. And inf S2, we don't actually have the machinery to properly deal with this yet, but hopefully, at least intuitively, you can see that these numbers are heading off towards 3, but they're never going to get there. No matter how large I make n, it's never going to get exactly to 3, but I can get as close as I like, and this is the kind of notion we'll be exploring a lot more carefully a little later on. But hopefully you can convince yourself that the infimum of S2 is equal to 3, which is not an element of S2. Okay, so supremum and infimum may or may not be members of the set in question. They're just the greatest and the least upper bound and the greatest lower bound, respectively. Okay, we have one more definition to work through. So this is the definition of maximum and minimum, which is quite similar to supremum and infimum, but has one additional caveat. So a real number A0 is the maximum of a set if it is an upper bound of the set and it's in the set itself. Okay, so similarly, minimum is a lower bound of the set, but it's also a member of the set itself. Okay, so you can see the similarity between supremum and infimum, and perhaps we should just belabor the point one last time with a little example. Compare 0, 2 and 0, 2. The open and closed intervals are 0, 2. Okay, so for 0, 2, supremum of 0, 2 equal to 2. Max doesn't exist. Whereas for 0, 2 with square brackets, the supremum of 0, 2 is also equal to 2, but the maximum value of 0, 2 is also equal to 2. So if a maximum exists, okay, let's put that over here. If a maximum exists, then it is also the supremum for a set. But it's possible to have a supremum and no maximum. Okay, it's similar to our example with the set 3 plus 1 over n. It has an infimum, but it has no minimum because the value 3 is not a member of the set. Okay, so just to practice working with the definition, we're going to do a quick theorem. So this is called theorem let A, so we're going to let A be a non-empty and bounded above set, and we're going to have a positive constant C. We're going to define this set CA by just taking multiples of each element of A multiplied by C, and then the theorem says that the supremum of this new set CA is equal to C times the supremum of A. Okay, so let's have a look at how we might prove that. So first thing we're going to do is figure out what we're actually being asked for here. So looking at the problem, we're being asked to demonstrate that a particular number, this number C sup A here, is the supremum of a particular set CA. Okay, so we've been given the set that we're trying to take the supremum of, and we're trying to demonstrate that this number C sup A is in fact the supremum of that set. So this is simply an exercise in applying the definition of the supremum and checking that this value satisfies both of the properties. So we need to verify that C sup A is the supremum of CA using the definition. This is why it's very important to know the definitions, because there's no other way of verifying this is supremum unless we check that it satisfies all of the conditions. Okay, so let's just scroll up for a second. Part 1 of the definition, just here if you're lost in the wall of text like I am, says that we must verify that the number is in fact an upper bound for the set. Okay, so part 1, need to show C sup A is an upper bound for CA. Okay, so how are we going to do this? We just need to show that that value is greater than every element in the set CA. So we need to be able to pick an arbitrary element of CA. So let C little a be an arbitrary element of CA. We can write it like this because that is exactly how the set C big A is constructed. So any element of C big A is going to be able to be written in the form C little a, so we can pick it like that straight off. Now we do have the supremum of A itself, which is sup A, available to us to use. So we know that A is less than or equal to sup A. So this implies if we multiply both sides of that inequality by C, CA is less than or equal to C sup A, as C is positive. Okay, so the inequality doesn't get flipped around because C is a positive number, and hence C sup A is an upper bound for CA. Okay, so we've verified part 1 of the theorem. Now I'm going to scroll up and look and see what part 2 was, and see if we can now verify part 2. So again, we'll scroll up to our definition, and we see that part 2 says that if B is any upper bound for A, then our supremum candidate has to be less than or equal to that upper bound. So we need to show that C sup A is less than or equal to any other upper bound. Okay, so the standard way to start this part off would be to just pick an arbitrary upper bound of CA. So let B be an upper bound for CA. Okay, now we're going to pick an element of A. Okay, why are we going to do that? Well, we need to turn this statement into a statement about A, because the supremum of A is the thing that we have, and we know that that supremum is less than or equal to any upper bound of A. But we don't have a corresponding statement yet for our set CA. So we're going to try and translate the problem back to our A set, use the supremum property there to show that holds for our set CA as well. Okay, it follows, so we've chosen an arbitrary element of our set big A. It follows that CA is a member of CA by definition, and hence CA is less than or equal to this upper bound that we chose at the start. Okay, thus A is less than or equal to B over C, as C is greater than 0. Okay, so just divided both sides through by C. I'm allowed to do this because C is a positive number, and that's how my inequality is going to work out. And this implies that this number B over C is an upper bound for A. Because remember, little a is an arbitrarily chosen element of big A, and it's less than or equal to this element here, no matter what my choice of A was, and so I have an upper bound. Now this means that the least upper bound, sup A, has got to be less than or equal to this upper bound B over C. And now we can translate back to our original space by multiplying this expression through by C. Thus C sup A is less than or equal to B, and hence C sup A, which we already established is an upper bound, is the supremum of CA. Okay, so we successfully verified both parts of the definition. One, that it was an upper bound, and two, that it is smaller than any other upper bound that you may come across. And we have another similar theorem here, which says that basically instead of C times A, we're doing C plus A. And in just the same way as the multiplication carried through the supremum under this multiplication, we can also do it with addition as well. So if we translate a set A by a number C, then the supremum of the translated set is equal to the supremum of the original set translated by that number C. I'm not going to prove this one. It's worth doing as an exercise. The strategy is pretty much exactly the same as for the previous question. You just need to verify that this number, C plus sup A, is the supremum of C plus A by checking it satisfies the definition. Okay, and we're going to prove one final theorem, which is an alternative characterization of the supremum. So this is giving an equivalent condition for what it means for a number to be a supremum, and that is if for every positive choice of epsilon here, you can find an element in your set that is less than, satisfying S minus epsilon is less than that element A. Okay, which means you can find an element between S and S minus epsilon for every choice of epsilon. Okay, so the picture that goes with this is, you imagine this, whatever's sort of the end of your set A here. Here's my S minus epsilon would be here. And what the theorem is saying is, no matter which value of epsilon you choose, you can always find a value of the set A that's in between these 2 points, is essentially what it's saying. Okay, so let's just double check, just to very quickly prove this thing. Now it's an if and only if proof, which is why I'm saying it's an alternative characterization of the supremum. So we need to prove both ways. So first off, we'll prove this direction, which means we're going to let S be the supremum. So let S be the supremum of A, and we're going to show that this if and only if thing is true. So we're going to choose an arbitrary epsilon greater than 0 and show that we can find that point. So S minus epsilon is not an upper bound for A. Okay, because S is the least of all upper bounds, so if I subtract anything positive off it, it can't be an upper bound anymore, which means, by the definition of upper bound, that I can choose an element greater than it. There exists A in A satisfying A is greater than S minus epsilon. Okay, so I'm using the fact that this, because S is the supremum, anything smaller than it cannot be an upper bound, and by definition of upper bound, if something is not an upper bound, then there is some number in the set which is greater than it. Okay, so that improves one direction. The opposite direction, we're going to say, suppose for every epsilon greater than 0, there exists A satisfying S minus epsilon is less than A. Okay, so now we're assuming the second statement, and we're trying to show that S must be the supremum. Let's just make that wording a little clearer. And A satisfying S minus epsilon is less than A. Okay, now we'll let B be an upper bound satisfying upper bound for A, sorry. Satisfying B is less than S. Okay, now we're trying to show that S is the supremum, so we're attacking this by contradiction. We're assuming that there is a smaller upper bound, and we're going to derive a problem here. Then, if we choose for our value of epsilon, that epsilon be equal to S minus B is positive, which implies that B is equal to S minus epsilon. This implies that there exists an element A satisfying A is greater than B. This is by the statement in the theorem that for every epsilon greater than 0, there exists an element satisfying S minus epsilon is less than A, which is our B. And so B cannot be an upper bound. Okay, so we assumed B was an upper bound less than S, and then we've demonstrated that it cannot actually be an upper bound. So hence our theorem is true, and hence the supremum, or S is the supremum of A. There is no upper bound, that is less than S.